please.
Okay, so thanks for coming. My name is Perez. I've been here at GISS for 1 year now. I'm an Earth Institute fellow. I have a double appointment with GISS and the IRI. So basically my background, I'm a modeler, but Earth Institute on a fellowship. I'm trying to look at the impacts of climate and dust on meningitis epidemics in the Sahel, which is an infectious disease, and there's a lot of speculation on the impacts of climate and dust, and whether if climate information could be used by international organizations to plan vaccination campaigns and other issues. So first of all, I would like to acknowledge my collaborators, Ron and Jan from GISS, and other people from Spain, NOAA, NCEP, France, WMO, and IRI. I will give you a motivation. I will try to describe a little bit the model development I did in the last few years, some validation of the model, and I will try to give you an overview of the current application of the model in the context of the meningitis studies. So, as you all know, dust is quite unique as an aerosol phenomenon. It's mainly one of the most it is one of the most important aerosols globally, together with sea salt. It affects climate, meteorology, ozone chemistry, biochemical cycles, but also on the short term, it can affect the quality, visibility, life and property close to the sources. So, the impacts and interactions of dust upon climate and meteorology span a wide range of spatial and temporal scales. When dust is transported, it affects radiation and cloud microphysics. At long time scales, it affects the ocean fertilization and also has an impact over the snow ice albedo. In the short term, also has significant impacts on atmospheric dynamics and physics, and on surface wind and turbulence, and on a feedback on dust emission. It has been shown that on the short term can affect its own emission by 15%. For example, there's a negative feedback of dust and dust emission. And also, for example, over desert surface, under huge dust storms, there's a significant impact on the short term of, for example, 6 degrees Kelvin near the surface. So longer time scales, it affects climate, and also climate affects on the larger time scale sources and vegetation, and in a feedback loop at dust emission. There are also human disturbances and anthropogenic forces in the whole picture. So one of the critical issues about dust is a global phenomenon. However, dust emission is a threshold phenomenon, sporadic and spatially heterogeneous, which is controlled on small spatial and temporal scales. So this is one of the motivations of my developments on the last few years, was to integrate a dust module in a unified atmospheric system, growing from meso to global scales. So the idea is to be able to provide global dust forecasts up to 7 days at subsynoptic resolutions, and nested domains at high resolution from 5 to 10 kilometers. Also to include intermediate complexity dust emission scheme with new high resolution databases, updated deposition schemes, and also introducing radiative flags between dust and meteorology. So the atmospheric core I'm using is the new model developed at NCEP, which is called the Non-hydrostatic Multiscale Model on the grid, which has been mainly developed by Garcia-Pando. It's an evolution of the old ETA model and of the WRF-NMM, which is the current operational regional model in North America from NCEP. And it has been spanned from these regional scales to global, so now the model is able to deal with global and regional domains. and it's intended to be an operational model, but also a tool for research to bridge the gap between meso to global scales. So the model is on a global latitude-longitude regular grid. There are some developments currently at NCEP looking at other geometries for the global model, but this is the current state of the model. And for regional, it's a rotated latitude-longitude. So it contains a standard physical package of NCEP, which has been thoroughly tested, the melogeomagnetic turbulence scheme, the Meningoccocal similarity theory for the surface layer with introduced viscous layer over land and ocean. Two possibilities for land surface model, the NCEP Non-land surface model and the LIS model recently developed by Tanchik. It includes as the operational radiation code is the GFDL, or although we have upgraded very recently to the RRTM in order to be able to include aerosols. As far as clouds, it uses the grid scale clouds and microphysics, which is intermediate complexity scheme, still rather complex, but still efficient for operations. And for convective clouds and convective precipitation, the Betz-Miller-Jančić convective adjustment scheme is not a mass flux, it's a convective adjustment scheme. So there have been recent upgrades to the tracer detection scheme, the gravity wave, the radiation, and this, the regional version of this model is planned to be the operational model this year in North America. So I'm going to talk a little bit on the developments we made to introduce the DAS model online coupled with this model. So traditionally, sources in models have been identified using land use categories of global databases. In fact, recently, like in year 2000, Prospero showed that preferential sources of dust could be were related to former dry lakes and enclosed basins, and he further refined the expression of so the identification of preferential sources in a model by using a function dependent on topography, which locates the topographic lows in semi-arid and arid areas. So this is what the model is using at a global scale in order to detect dust sources. As far as the soil texture, so the soil particle distribution that will be used in the emission scheme, we use the new StatsGo 1 kilometer database, and we distinguish between among 4 particle types: clay, silt, fine medium sand, and coarse sand.
Is that surface texture?
Yeah, it's a topsoil texture. Yeah. So so it's topsoil texture, and we use the soil texture triangle plus other criteria to distinguish, because the texture triangle distinguishes between clay, silt, and sand. So we add further criteria to separate between fine, medium, and coarse sand, which I will show it can be useful for the dust emission scheme. So there are many ways to treat the dust emission in models. There are very simple schemes to very complex schemes. Ron is laughing. So the simple schemes try to assume that we have a lot of uncertainties on the soil textures, a lot of uncertainties in the surface winds. So they try to simplify the dust emission by diagnosing the emission flux as a function of wind speeds and other parameters, but they don't try to model explicitly what is observed in laboratory studies or wind tunnel studies. So in particle motion, we can distinguish 3 modes of we can distinguish 3 modes of motion: the creep or rolling of the largest particles, the saltation or horizontal motion of large soil grains, and finally the suspension of dust. So what is observed is that the friction velocity above which there's a motion of particles has an optimum between 60 and 80 micrometers, decreases for particle size below this value and increases above this value. So the point is that here interparticle cohesion forces of the small clay particles make difficult the direct suspension of dust to the atmosphere, and here gravitational force is doing the same but for the largest particles. So there's an optimum here. So, but what is long range transported is this fraction over here. So how this is ejected to the atmosphere is through saltation, through some blasting of the large saltators to the dust particles. So in order to express that in the emission scheme, we separate, we distinguish among the horizontal dust flux or saltating flux, which depends on the 4 particle size that we have shown previously, depending on a function which was derived by White, semi-empirically, and depending on the thresholds with this function of each particle size, and on the relative surface area content of each particle on the bed of particles. The friction velocity, the threshold friction velocity, depends on the threshold friction velocity of a dry and smooth surface, which has this shape here, and is corrected for soil moisture effects and drag partition, which takes into account the fact that the bed is not always smooth, and so stone, pebbles, and rocks can decrease the momentum that is available for particles, erodible particles to be emitted. So the vertical dust flux, so there are many complex models that after these horizontal flux, they try to model the flux in a complex manner, so in order to get the size distributed dust from the sources, and depending on soil, on energy, depending on the kinematic energy of the saltating particles, and also on the binding energies of the clay particles that are there. So this is very complex, and at regional and global scales, there's no data in order to do that. So what we do is to simplify, and we relate the vertical flux to the horizontal flux with the horizontal, what we call the horizontal to vertical flux ratio, which depends on a constant depending on the population of each of the particle size in the soil and their mass fraction in the soil. Finally, what we assume, since we don't have a scheme that gives us the size distribution of the dust explicitly, and we obtain a total flux, we distribute on the size rings of the model, take into account assuming a constant trimodal size distribution of emitted dust, typically measured at the sources. So finally, in summary, the vertical flux is related to horizontal flux with this horizontal to vertical flux ratio. This is related to the size distribution, and this term here, it's a tuning parameter, the source function I shown before, and a factor which depends on vegetation, which gives us, which has a seasonal dependence. So
the tuning parameter?
Tuning parameter.
What is that?
Yeah, so we have.
I have to ask this.
Yeah, sure. That's I would tell you that's the most important aspect of the DAS model. And in fact,
I would guess it is.
Ron has a very convenient method in order to retrieve this parameter. The idea is that we have a lot of uncertainties on the dust emission process, of course. And so what we try to do with this global tuning constant parameter is to try to reduce the global error when we compare against the wide range of observations. That's it. So we tune this parameter in order to match the concentrations close to sources, far away from sources. So we assume that everything else is correct in the model, and we tune our emission scheme.
This has to do with the spatial inhomogeneity of sources?
No, it's just it's a simple it's a global tuning constant. For example, if you increase the resolution of the model, your wind speeds will usually then increase. So this changes the the estimation of the fluxes, and
so this has to do with resolution.
has to do with resolution and other uncertainties. But I'm saying if you change the resolution, you're changing the winds, you're changing the estimation of the magnitude, maybe not so much the spatial patterns, but very much the magnitude. So you have to tune this against available observations. So I will talk a little bit about this later.
Can I just ask about,
Yeah.
you said that the vegetation cover is seasonally varying? Or
Yeah.
does that mean the source regions or source areas are seasonally varying? And why?
Sorry. It's not Windows, huh? No, again, please, sorry.
The vegetation.
Yes.
Correction.
For vegetation, we use, so somehow these two factors, this is the source, this is the probability that you have. So 0, you have no source. 1, you have maximum probability of having a source there. And this is telling you 1 minus vegetation is the part of the grid cell that is not covered by vegetation. And this is seasonal, monthly varying. I use a monthly database, and I interpolate the monthly value between 2 months to the day I'm simulating. So it's not, it's a climatological database. There's no interannual variability. Just.
So that's assuming that vegetation is changing the source, dust source.
We're assuming that, yeah, we're assuming that where we have vegetation, that it will be more difficult to have uptake of dust. That's an assumption. Usually, it's the impact of this factor is not very, very, very important because in the model, so these sources here, we usually identify the sources, what we call so-called natural sources, okay? And most of these sources are natural, arid deserts, natural deserts. So, for example, here in the Sahel, there's a part here of the Sahel which is dry and might be a source which is not identified in the model. These are what we call anthropogenic sources because emissions or erosion there is due to land use change through time or past droughts, and there's a seasonal varying vegetation that might affect the emission. So that's a critical issue in dust, anthropogenic sources. So in this model, for the moment, we don't have this estimation. So I will go forward. So just talking about a little bit about advection diffusion. The advection in the model is Aurelian, conservative, positive, definite, and monotone. I will just cite Savage is using Crank-Nicholson for vertical advection, and the modified Adams-Watford for vertical or horizontal advection. The dust and whatever tracer in the model follows these schemes. Also, the vertical diffusion scheme, the vertical diffusion in the PBL is handled by the surface layer scheme and the boundary layer parameterization, and lateral diffusion is formulated following Margaret-Skin linear approach. About sedimentation and dry deposition, very quickly, we use the Stokes-Cunningham approximation, which is mostly used in most of the models, and for dry deposition, parameterization of Sang et al., which takes into account gravitational settling, aerodynamic resistance in the turbulent layer, and surface resistance in the viscous sublayer, including Brownian diffusion, impaction, and interception. Concerning the scavenging from clouds, the model distinguishes among grid scale and convective clouds. For grid scale, the model uses Ferri microphysics, which includes some of the complexities of fully complex microphysical models, but still some simplifications in order to let the model be operational. So I will not go into details. If somebody is interested on learning a little bit more about this parameterization can come to see me. But concerning the aerosol, we model the scavenging, take into account in-cloud and sub-cloud scavenging, and also the release of dust in the column due to precipitation evaporation. So just very quickly, in-cloud scavenging includes, it's depending on the autoconversion rate of cloud water to rain, mainly, and balanced by the fraction of water in the cloud. And depends also on the melting of ice, into precipitation, balanced by the fraction of ice in the cloud, and also depends on the solubility on an assumed solubility of the dust. There's a lot of uncertainty in this parameter, and depends on the chemistry. The model does not include chemistry, so we assume a constant parameter depending on particle size, and assuming a balance between the purely hydrophobic or purely hydrophilic assumptions. And concerning to cloud scavenging, we use the scheme of SLIN, which includes the collection efficiency of particles depending on the size of the aerosols and of the droplets, and also on the precipitation rate. This parameter is rather, rather complex. It's a semi-empirical relationship, including directional interflection, inertial impaction, Brownian diffusion, and it's included in the model through lookup tables to increase the efficiency of the model. Concerning below cloud scavenging, a similar relationship of SLIN, take into account the diameter of the snowflakes, and similar relationship take into account those factors. Finally, and this is a little bit quite, a little bit different from other models. Usually models include a mass flux scheme for convection. And traditionally, the ETA and the NMM, the WRF-NMM and the NMMB use the Betz-Miller-Janji convective adjustment scheme, which regards convection as a thermodynamically driving process, putting heat and moisture up, driving up moisture to reduce conditional instability. And of course, it does not describe the transport between the layers, but it just describes the change of humidity and heat within the convective cloud. So in practice, what the scheme does for temperature and humidity is to relax the pre-convective humidity profile towards a reference profile that is observed in nature. And in fact, during the convective time step, assuming a relaxation time and a factor here which depends on the convective regime. So what we do for dust, I haven't seen that in literature, but so this scheme has been tuned for many years at NCEP and give very good skills concerning precipitation. So rather than implementing a new mass flux scheme into the model, I decided to follow the scheme of the model and trying to do something similar for the aerosol. So what I did is I created a concentration reference profile which I didn't observe in nature after convection. What I am assuming is that the reference profile of dust follows the shape of the reference profile of humidity, and we do the same procedure. We nudge our pre-convective concentration profile towards its reference profile, which is assumed to be has the same shape as this one here. So it's a huge simplification. I admit, a lot of criticism, but that's the only way I found in order to couple both schemes.
The reference profile of humidity has the sharp drop off with height because of the temperature.
Sorry?
The reference profile of humidity has a rapid decrease with height because of the thermodynamic control on humidity. There's no thermodynamic control on dust. So is the reference profile of dust also dropping with height like the
we're assuming that we're mostly assuming that the redistribution of dust after convection, so you have an amount of dust within your convective cloud. We're assuming that after convection, the redistribution of dust follows the redistribution of the humidity. And you're right, I mean, dust is not a thermodynamically driving process. We're just, I don't know how to call it, mimetizing the behavior of
I mean, it's true that the dust is going up in updrafts where a lot of it is getting rained out.
Okay, so that's the issue. I'm telling you that how we're doing this is, okay, there's another criteria, which is, one is we assume the shape of the reference profile of moisture. But of course, we perform in-cloud scavenging within the convective cloud, and this in-cloud scavenging is proportional to the decrease of humidity within the convection within the convection time step within the convection cloud. So this is negative because this is always negative. There's a decrease of moisture. If we're in deep convection, there's a decrease of moisture and a production of precipitation within the convective cloud. So we have an amount of dust within the convective cloud. We release an amount of dust proportional to the release of moisture. And then we assume that at the end the dust will have a shape with a magnitude, a global magnitude, which is how do you say, which is managed by the fact that we have released concentration here, and it has the shape of the humidity profile. So I mean, there are a lot of simplifications in the future. So this model is within the NMMB system of NCEP, and they are kind of, this is in the Earth system modeling framework, so we will be able, maybe in the future, to try a mass flux scheme. But for the moment, I decided to simplify the things and keep this.
So, excuse me. So, the dust coming from Africa and going to the Caribbean, for example, I would be surprised if this would give you appropriate flux coming across the Atlantic, because you seem to keep it out of the layers where I think it's transported. I mean, the humidity falls off so rapidly, the specific humidity falls off so rapidly with height that I would be surprised if the dust distribution looked anything like that.
No, it's only under deep convection.
So this is only in a subgrid?
Yeah. It's only under deep convection.
Oh, okay.
It's not dry convection or whatever. It's only when you have deep convection and deep, high convective precipitation, you have these updrafts. This is the only, then for shallow convection, what we assume, there's no precipitation in shallow convection in the model. We assume an homogeneous mixing within the cloud.
So what gets dust up to the deep high in the troposphere? Is it not deep convection, or if it's dry convection that gets it up there?
No, it's deep convection. Yeah.
So
well, then
it's deep convection, but also
like
it's deep
legitimate
convection.
concern.
No, it's deep convection. But it's also, there are other processes, but deep convection is just one of them.
But the point is that
this tuning parameter C is a single constant.
Right,
it's not a function of height.
No, it's a tuning parameter of the emission scheme.
Just for the emission.
Yeah, just for the emission scheme. I will show you some results now, so we can discuss. And
It was successful.
yeah, because this is that blah blah blah. So just a note. This is that the model didn't include. The operational model at NCEP, they're interested on the short term, on the meteorology. So they were assuming, for example, the aerosol effect in the past was 3% reduced. They were reducing 3% the solar constant in order to take into account the global effect of aerosol. So this is what they were doing. And they were using the GFDL old scheme, which was quite tuned, but we couldn't add the aerosol, so we changed it. I changed it and put the RTM with aerosol. So for the moment, the model includes the dust online, and it has climatologies for other aerosols. So now I'm going to show you a little bit some validations of the model we're performing now in collaboration with Aerocom. So first I will show global yearly averaged values. These are, here we can find quite a lot of stations which are on the main transport path of the dust from Africa, from Asia, Australia. Also, we have these stations here to account for the emission in South America, and also background stations here. What we can see here, there's at this point, this model hasn't been, has just been manually tuned. I'm planning to use Ron's optimizing code in order to tune the model more finely. But somehow one of the problems of the model at this point, this is a 1.4 by 1.4 degree resolution driven by reanalysis. Here you can see on the background stations, the model, I mean, we're talking about 0.2 microns per cubic meter, which is a very low concentration average, but still the model is kind of overestimating the amount, and probably, you know, one of the candidates to look at is convection and precipitation. So very probably. So I'm looking at that, trying to tune. I have many possibilities to tune the model through the solubility constant, or looking also at the convection scheme. This is the comparison with optical depth. What the model shows is that the transport over the Atlantic is correctly captured. What we are maybe overestimating is the dust content close to the sources here. But still, this comparison has been done with the monthly averages for the moment, and so now I have I'm trying to do that with using the monthly averages of measurements and monthly averages of model. And what we know also from Aeronet is that there are a lot of missing points. So we're going to try to really use to make a comparison of what we observe and what. For the moment, this is preliminary comparison. This is for year. This includes observations, acclimatology observations from '96 to 2006, and this is for 2000, so the year that is simulated. But the pattern still remains the same. We have some overestimation very close to sources. Finally, this is the deposition network. In general terms, the model, although it overestimates, it reproduces the shape. However, it overestimates in these stations here. But this is quite curious. I mean, if we compare, I haven't included here, but if we compare what happens with all other global models, we have the same overestimation in all the models. So we're trying to understand if there's a problem with the measurements. There's a lot of uncertainty. In fact, this is total deposition, wet and dry deposition. So I mean, I wouldn't believe completely these comparisons. And this is, I'm showing you here very shortly, regional simulation at 0.25 by 0.25 degree resolution versus Aeronet for the regional domain, North Africa, Middle East, and Europe. Daily variability of the optical depth for 2006 for different regions. So this is the Mediterranean, let's say this is Italy, for Crete this is Eastern Mediterranean and Greece. So as you see, well, I don't know if you see it very much, but the model is in black, the total optical depth is green, and the coarse optical depth is red. So you have to compare red with black. I'm sorry I didn't quantify it still, but you can see that the model follows really good the daily variability of the dust. Here, this is the Mediterranean. As you can see, these are anthropogenic aerosols, but the coarse aerosols are really well captured. Daily variability. This is the Iberian Peninsula. You see here. For Arenosillo, Granada, and Cáceres. This is the eastern subtropical Atlantic, so La Laguna, Santa Cruz, and Izaña. Izaña is overestimated because it's at 2,500 meters, but still the variability is very well captured. And this is North Africa and the Sahel. So this is North Africa, Blida, again. This is the Sahel. The Sahel is a little bit more complex. There's some underestimation in winter here. This could be due, for example, to these anthropogenic sources in the Sahel, which are not included in the model. There's some overestimation in summer, and here it's rather well captured. And for Niamey, which is a little bit north from Ilorin, really the variability, the daily variability of the model is rather well captured. And this is finally Middle East, which is maybe the worst the worst results here. For example, these high peaks are not captured by the model. This is maybe due to sources, maybe due to the fact that the model, the mesoscale model, is not able to capture some of the episodes, or maybe also could be internal mixing of aerosols. So in this signal of the coarse AOD captured by and measured by the photometer, or the algorithm that I mean mainly is not doing well. But I really don't know. So I explained a little bit the developers of the model, and now I will go a little bit to something that it might not be very common here, but that's what I'm trying to do with the IRI, which is to apply this model for something very applied, which is health impacts. So traditionally, aerosol models, or there are some studies in science which try to see the health impacts of aerosols, so respiratory, or so. This is a different thing. We're talking about meningitis. Meningitis is a very nasty disease, which happens which is epidemic in the Sahel. I mean, of course, in many places in the world, but really in the Sahel, it's really very huge. And there has been a lot of speculation. This is an article in Science 2008 talking about the ill wind bringing meningitis. So in winter, in the dry season, you have the Harmattan winds blowing from the northeast. And so associated with these winds, I mean, there are upsurges of meningitis in the countries affected by these winds. So there has been a lot of speculation of what is driving the disease, what are the risk factors, and if we know the risk factors, we can help preventing or also helping WHO in their reactive vaccination campaigns. So what is, and another question is, if this is related to Harmattan, what are the factors, the mechanisms that are driving the disease? This is humidity, this is dust, this is the temperature, this is a combination of factors. So I will just let you know some key things about meningitis. There are different forms of meningitis, but we're talking about the bacterial form, which produces a serious infection of the thin lining that surrounds the brain and the spinal cord. So the bacteria is transmitted person to person through respiratory droplets. There are 12 serogroups. 4 of them are existent in Africa. This is what we call the meningitis belt, where the highest rate attacks occur. 80% of the global burden is there. So there are 21 countries and 300 million people at risk, and there have been 700,000 cases in the past 10 years, with 10 to 50% fatality rates, and 10 to 20 of survivors suffer permanent brain damage. So there's a polysaccharide vaccine which is available, but it doesn't provide long-term immunity. So there's no vaccination throughout the belt. It's just reactive vaccination. This means when an epidemic starts, WHO decides to may perform vaccinations in those districts. So sometimes it's too late. And there's a plan for the new conjugate vaccine this year, but in order to, which will provide longer immunity to the belt, but full coverage of the belt will not be available until 2020 or 2025. It's a matter of money and resources. So this is what I was talking about. You have the Harmattan winds in the dry season. And this is a study of Sultan, which relates the disease to the Harmattan index. What we have is dust coming in winter in this direction here in very low levels. So dry air masses from the north with dust, and here we have the monsoon winds with biomass burning particles towards the north. But the problem to study these issues is that not only climate is a factor, not only, it's very complex because there are many other risk factors that come into play. We have climate, so possible risk factors could be humidity, dust, wind speed, temperature, lack of rainfall. which also at the same time are related and so are correlated, so it's very difficult to see what, in fact, this is not like malaria. We know the mechanisms by which malaria develops. With meningitis, we still don't know, and this provides further complexity. There are other health factors, for example, number of years since the last outbreak, the ongoing outbreak in the neighboring district, the vaccine coverage, etc., and other social and demographic factors like population density, proportion of children under 11, and other issues. So what we're trying to see and what kind of information we can provide to the health community from our point of view. One is they have what they see in the data of meningitis cases is that they have large-scale waves from 8 to 12 years. This could be due to changes in immunity in the belt, but also could be due to climate. So decadal changes in climate, for example. So they ask us if we can say something about that, and also if we can tell them something of what's going to happen in the future. So that's what they ask for, okay? So for example, other issues is if they have to predict a little bit in advance what kind of vaccine production they need for the next season. Is there some predictability of the dry season with seasonal prediction models? In the Sahel, mostly all the research has been done for the humid season, for the rainy season. There's not too much research done for the dry season, so that's something to be assessed if there's some skills for the dry season. And the most, and that's what I'm really working on, is the operational district levels. Is adding climate criteria in the reactive vaccination decision process at the district scale helping WHO to prevent outbreaks of meningitis and saving lives every year? So this is what we're concentrated now. As I told you, the procedure is the following. Each district in the Sahel, they have a surveillance, and they measure the number of cases. When they reach 5 cases per 100,000, they are in alert threshold. So here, they still don't do anything. They just verify the cases. And it's when they reach 10 that they decide to go there and do vaccination. What happens is that when they decide to do this, sometimes we are here already. So can we, providing climate information and other, so providing a model which could somehow predict, can we tell them, can we communicate probabilities in order to help them take the decision before? This is one of the key issues. Okay.
So you said some correlations, and what's the physical mechanism or physiobiological chemical you get?
Before, may I ask, how long does it take for a vaccine to work?
How does that, what is that?
It's immediate. I mean, it's like, well, I mean,
if you are not infected, you will not be infected immediately.
if you're
So
not
there is no
infected,
yeah, if you are already infected, then that's it. But
yeah,
if
but
you are not infected, the vaccine works immediately. So if when going up this curve, you just have to, you really stop it the moment you
you mitigate, yeah, and sometimes you stop. Yeah, it depends. Yeah, I mean, it can be very nasty. So I mean, the problem is very complex. But you have carriers of the bacteria, and some of them which are more susceptible, they develop the disease, and some others do not. So we don't have information about the susceptibility. We don't have information about, you know, many of the issues of the disease. So, for example, it's very difficult to investigate the disease through epidemiological models, you know, with the typical framework of susceptible, infected, and ill, you know, and there's a kind of models to do to simulate that, in which we could introduce the climate information in order to help to understand the disease.
Are there any animal vectors, or is it only human?
Sorry?
Are there any animal vectors?
No.
You showed before some time series of dust in the
I'm going to show you
Is
now.
that correlated with meningitis?
I'm going to show you some stuff now. That's very preliminary things, but I'm going to show you. Okay. So there's been a lot of speculation. There have been some studies using satellite information on the Sahel, which is column integrated, putting there out some correlations with meningitis, but at the seasonal scale, you know, and you know, more or less everything correlates at the seasonal scale because you have the harmattan, and you have the humidity, you have low temperatures. Because I mean, usually in the urinals they say the hot and drier masses driving meningitis. No, they are not hot. They are the lowest temperatures during the year, in fact. So a lot of speculation there, and people not experts on climate or dust using data like, you know, aerosol indexes and stuff like that, which is very uncertain over there, and you know, it doesn't make much sense to directly use that. So that's what we are trying to model, the respirable concentrations of dust on the belt on the last 30 years, but not from a climate point of view, but trying to model the daily variability. So that's what I'm going to show you. So here, the hypotheses that link that, these are just hypotheses. Nobody has shown this yet. So possible mechanisms is that the irritation and disruption of the epithelial lining of the upper respiratory tract allow bacterial penetration. So the dust gets into the body, damages the mucous membranes, and allows the bacteria to penetrate and to provoke the disease. Enhancing bacterial survival via iron content of the dust. Wow. You know, a priori, meningitis, when it's in the air, after 1 hour dies. So this is why this hypothesis, serving as carriers of bacteria, is highly improbable. Although there are some measurements in soils that measure meningitis. You know, so it's really, I mean, it's really complex.
As for one, they show that smokers have a higher risk?
Yeah, in Western countries, yes. Yeah. So this has been shown for Western countries. So there might be something there. Okay. And another issue is behavioral. You know, when you have the huge dust storms in the Sahel, people get together, you know, there's crowding and there's more contact to contact. Okay, so.
But they have to be sick already.
Huh?
I mean, somebody's got to have meningitis already.
Yeah.
In fact,
carriers.
not just one, but some fraction of the population.
Yeah, yeah.
The herd.
Yeah.
Not herd.
So that's what we're doing now. That's what we are doing now. We have performed with the GISS model and with this regional model. The GISS model has been run by Jan, nudging towards the reanalysis. So our idea is not to have climate simulation, but to have something like mimetizing the observed values. So we want a reanalysis of the past to understand the whole thing. So we have two simulations. One has been done by Jan and Ron, and I also used the model, the regional model. So at 0.5 degree resolution, I performed a 30-year simulation from 79 to 2010. We have our first meningitis record at the district scale on the 80s. So the simulation was reinitialized every 24 hours with 12 hours in-up. So, and we used to drive the boundary conditions and the initial conditions reanalysis to data for atmosphere and the NASA GLDAS for soil. And we have 3-hourly output of climate, so humidity, temperature, humidity, precipitation, whatever, and dust concentrations. So, and you know, what we're trying is to compare with weekly cases at district levels in Niger. We have data for 39 districts in Niger, weekly cases of meningitis. So in order to understand the influence of climate and dust on epidemics, and to build together with other risk factors, other data that we have, to build a statistical predictive tool, if possible. So here I will show you some preliminary results. This is just from the open, so I'm going to speculate a little bit. So here you can see the average number of cases per 100,000 over the belt in black, and this is 86, this is 2008, versus precipitation, which is in green. Here this is in one district, This is average for nitrogen, this one district, wind direction. So here you can clearly see the seasonal cycle of the disease. You have the peaks, no precipitation. When the precipitation comes to the belt, there's a sudden decrease of the cases. So here, this tells you that climate is an important factor at the seasonal scale. Okay. As you see also from the data, you can see these large-scale waves in the disease. The idea is, can we explain at least part of this signal with climate information? I still don't know. We have to do a lot of analysis of the climate data, but
cherry picking, you got one wave, but these next waves didn't look so good, huh?
sorry.
It seems like you're cherry picking that first wave. When we have a huge pulse later, it's like nothing going. There's no correlation.
Where?
I thought you said distance.
No. I'm not saying there's a correlation. That these large-scale waves are related to precipitation. I'm not saying that.
Okay.
I'm saying if we can understand, not with precipitation, but with other climate analysis, if we can interpret these changes in the belt through, at least try to understand. But of course, I'm pretty sure that these scale waves are related to the immunity of the population, or a combination of factors. That's a really difficult issue here. So here you have wind direction. You clearly see the harmattan preceding the peaks. Okay. Absolute humidity. Again, you have a reduction of absolute humidity, and after a while you have a reduction and you have an increase. Reduction, increase. Okay. We can clearly see, and this is 2-meter temperature, and here is dust concentration. Okay. First, if you observe the dust concentration values here, and you compare with what's happening with humidity, first of all, you can see that dust is much more noisy than other climate variables. So this is one of the first things. We have mainly before the season we have a huge transport of dust here, but also during the season or after we still have dust transport. Here you can see during the season or before. So if we're going to correlate absolute humidity and temperature with cases, what's going to happen, first of all, if we correlate the whole series, there's going to be a seasonal signal in our correlation, which is going to be clear. However, if we correlate dust directly with, so weekly average of dust with cases, what's going to happen, this is a very noisy signal, so maybe we would need to do extra work in order to do moving averages and stuff like that. So what I did for the moment, I'm plotting here scatter plots of humidity, absolute humidity versus cases. This is integrated for the whole Niger. This is at lag 0 and up to lag 12 weeks before. So we're trying to understand. We need to understand that absolute humidity. So if there's a climate impact on the disease, we're going to see the response a little bit after. So if we have low humidity conditions, we're not going to see straightforward a peak in that. So that's what we're doing lag correlations. So here you will see, okay, you reach 12 weeks before, you reach a 0.3, minus 0.3 correlation. You just say, oh wow, this is nothing, right? We're used in our community, we're used to work with 0.7, 0.8 correlation values. What happens here, however, is that if you see the huge epidemics, or you can see here that there's a part of the distribution here which is concentrated here, and you can really see that the value. So the huge epidemics are only given at certain humidity conditions. That's already something that could be used by WHO. If you are in this regime of humidity, it's highly improbable that you can have a huge epidemic. So this really simple exercise already can give a lot of information. So for the moment, what's the problem here? We can have very low humidity conditions and have no epidemics. Of course, there are many other factors influencing which are not taken into account in these correlations here. But first of all, what we can see here is that 12 weeks in advance we can have some information. So this is important because this is useful for preparedness. Okay, so we are not talking about the same week to the same week, but here we can have some information.
Did you do like the whole year, for example?
No, this is only the dry. This is only the dry weeks. I
wonder what it would look like if you did 52 of those.
No, I took out.
Guess.
I took out this here. Of course, if I put all the data, it's going to be the correlation is going to be very high because you have the seasonal signal. I just use the 4 months in winter, December, January, February, March.
So hasn't low absolute humidity been linked to flu outbreaks?
Yeah.
So how does that? Is there a similar time scale with that?
There's
Outbreak and the meningitis?
There are some studies linking flu with meningitis, and this is a risk factor. And in fact, but there's no data. That's a problem.
I thought, like, Jeff Shaman, who was at Lamont like some years ago. Did
Yeah.
you work on that?
I don't know him. I know that there might be some data in one specific district, but we don't have large, available data on a spatial relevant scale. So of course it's a risk factor. We are not, again, we don't know the mechanisms. Maybe, people that get flu, are more susceptible to, if they carry the bacteria, to develop the illness. So there are many speculations, but we really don't know. I mean, I'm not a health scientist. I've been with them like in hundreds of meetings and they really don't know.
Carlos?
Yeah.
Can you wrap up?
Yeah, sure. I will wrap up. So finally, this is absolute humidity, just temperature. Temperature, it's, you also see low temperature for the huge episodes here, and with some time lag. And finally, for dust, we don't see any specific, first order relationship in the sense of huge episodes are not related to huge dust episodes. But again, this is very preliminary. These are weekly average concentrations. As you have seen, the signal is very noisy, and I'm comparing week to week and lagged week to week. So now what I'm going to do is to try to accumulate the variables. For example, what was the dust content during the last month? Or what is the frequency of very high episodes, because the very high episodes can be behind of, we are going to speculate a little bit with the data. Let's try hypotheses, for example. And of course, use this in combination with other risk factors. It's a very complex issue. I mean, it's rather frustrating when you get out of your field of research and you try to connect with this, but it's interesting at the same time. So if you have more questions, comments, and suggestions, I welcome them for sure. Thank you.
Have you tried or plan to try any factor analysis, like certain percentage of dust plus certain percentage of rainfall or things like this?
Yeah, this is regression analysis. I'm on that, and I'm showing you just integrated for the whole country for Niger, and we have 38 districts, and we're trying to make regression analysis combined with different variables, but not only climate, also, for example, population density, urban or rural population, many other issues that we have. So that's what will be working on the next, the next months.
Are you working towards doing like a forward model of the disease? Because you did a nice explanation of forward modeling dust.
Yeah.
Are you also going to forward model the disease outbreak more than
Yeah.
just do
Yeah. So there are three. I'm learning quite a lot on that now. I'm not an expert, but I can tell you there are three more or less framework we can work on. You have the classical epidemiological models. Infected, susceptible, ill. And death. And but in order to really use this kind of epidemiological models to understand and to eventually predict the disease, we don't have data. So if you simplify those epidemiological models, you know, because you have to assume, for example, that you don't have the population of susceptible. So you just assume that susceptible is an amount of your population, for example. No? So at the end, if you reduce those equations, you find out that the model is not more than a regression analysis of your cases is equal to a linear relationship to whatever information you have that can correlate with that. You know, so this is the, and then there's another way which we're collaborating with the University of Lancaster. There are people that are looking to the predictability of the disease, just looking at the cases. So with autocorrelations of the data. So this is purely statistical, kind of rather complex modeling. But the idea would be at one point, for example, to use their framework and to couple our climate information to their framework, to use both kind of predictability frameworks and put them together so we can give something that can be used. So yeah, it's really difficult because you have, on the one side you have the research side, but on the other side you have the operational. You know, for example, now I'm going to go to Addis Ababa next month, and you know, WHO really, they ask for very simple and, you know, very accurate, simple and accurate ways to decide. You know, because now they are deciding like this. That's it. I mean, they are deciding by experience, by what they know about the disease, or we think that Burkina this year is going to explode. Why? I mean, they just feel it. So that's what we're trying to give them, a little bit of more scientific support. But still, I mean, it's frustrating, of course.
You made a quick comment about the fact that people know a lot more about malaria. What did you mean by that? Do you mean
I mean that the mechanism is well known. It's a mosquito, and the mosquito has, you know, some characteristics of the climate where it survives and where it dies. This is quite well known. So the most uncertainty in the malaria, one of the huge uncertainties in malaria is the climate. But in meningitis, climate might be one of the less uncertain parameters. So I mean, when the health scientists see this kind of series of climate, they are, oh, that's data. We have data, you know. If it's reliable, completely reliable or not is another issue, but that's data at least. I mean, very uncertain, but we have data. So, but for malaria, they know there are mechanistic models of how the disease, of the dynamics of the disease. And mainly for malaria, they try to see how interventions like putting nets can change, for example, the dynamics of the disease, etc. So they are much more advanced. It's also true that malaria is a huge, it's more huge than meningitis. Malaria is the top one. You know, many people are working on that. Many people. Yeah. So I think that for meningitis, what you're saying is why we don't know why. I mean, there are no in vitro experiments. We don't know how the bacteria, why the bacteria gets into the system, why there are some carriers and they don't develop the thing, and why there's some others that they do.
What do you mean you have symptomless carriers?
Huh?
Symptomless carrier, healthy carrier.
Yeah, sure.
And what are these bacteria, where are they living during the wet season when there aren't very many cases?
Sorry?
It's an oversimplified question, but where are all these bacteria living during the wet season when there are not very many cases?
So now there's a project which is paid by Bill and Melinda Gates, because they are very, I mean, they are putting a lot of money on infectious disease, which is called Meningoccocal, which is they are trying to see what is the carriage during the wet and dry seasons. Can you believe that there's one study in literature about that, and saying that it's mostly constant during the year, the carriage? So that's why we think that climate, the action of climate, is not about transmission, but more about getting people more susceptible. But there's a reason, for example, there's a recent paper in PNAS talking about, it's flu? Yeah, it's flu. And we still don't know in the Western countries what is the climate factor which drives the flu. We know that that's seasonal, but it could be behavioral. We're just together in winter, so but also humidity might have an effect on transmission. And this PNAS article talks about that. So it's very,
Correlation is not causation.
exactly.
That is the problem.
Yeah.
There's so much correlation, but maybe none of it's the causation.
Thanks.
Thank you.